SARvision Biologics comes with a number of files to help you get started. If you look under the main menu, Tools, Open Resource folder, this will open a directory on your Windows machine where files can be found that will help you get started. These include several sequence files in CSV format, a residue table, and a modifier table. Of interest to this particular video is the somatostatin sequence dataset. So we will open this one by going to File, Import Sequences, and we can navigate, you can copy and paste it from that window. We will navigate to that same directory to open this dataset, the somatostatin sequences.csv. When we open this example dataset, you get a load data dialog that gives you a quick summary of your data. This data contains two sequence columns. We can choose either one, the sequence in Helms format or the sequence in R format, and any number of data columns that can be associated with your data. In this case, we have several receptors, 1, 2, 3, 4, and 5, identity of each particular sequence, and then some other data that it comes along with the data file. We are going to perform alignment, so we will keep that button checked. We hit OK, we get another pop-up that's asking us about alignment. There's many ways you can align your data. In this case, we're not going to align it to our reference sequence. We're going to align it to our using Clustal. We're going to do a multi-alignment using Clustal. And for our reference sequence, it can be any sequence in our data set. We could pick somatostatin by default, the first one, or we could pick any of the sequences that come in our data set. For this case, we'll pick somatostatin 28. And when we're done, we can just hit OK. And the program imports the data, parses the sequences into into a sequence data set. So it identifies each residue in the sequence and then puts them into a cell in the data table and performs the alignment. So it took the sequences and ran them in Clustal to get a multi-alignment, one sequence per row, and shows them on the right. On the left is our data, any data associated with these molecules, and on the right are the actual molecules, the sequences that we are of interest. This is kind of cluttered, so the first thing we will do is right-click on the Sequence Table tab and come up to Columns and open that. And here we will hide anything that's not of interest to us. We're only interested in the identity, the ID of each sequence, and then the data associated with it. And we can lock any of these to the left so that we can scroll past them, and we can hit OK. So now we have a nice clean data set. And as we scroll to the right, the first two columns remain frozen. Notice in this data set that some of the sequences have a 1 in front of the cysteine. These are designating macrocycles. This cysteine is bridged to the cysteine at the 28 position. Note that some of the residues are in red, whilst others are in black fonts. Some are in green fonts. The residues that are in black fonts are the natural amino acids. Those that are in red or green are the unnatural amino acids. This is all under the user's control in the residue table. The background is white if the sequence matches the reference sequence at the top. If you remember, we chose somatostatin 28, so there's 28 residues on top for somatostatin. And it checks the alignment to see if there is identity to the reference sequence. For example, on column 23, these lysines are all colored in white for a background. However, in column number 22, those residues that are not tryptophan are highlighted in yellow. So all of the residues, the mutations, are colored in yellow, highlighted in yellow. You can right-click on any column to get a menu of options for them. You can perform sorting, you can perform a heat map, or any of these options. To do a heat map, you simply select the heat map, and you take the range of values that you are interested in. For example, we can go from green to yellow, and these would be acceptable values for this particular data set. And then we can add another column, and we can go from yellow to red. And we could say the max should be 200. Anything over 200 should be red, undesirable. Anything close to 0 will be green. And then between 0 and 200 will be a yellow, giving us a gradient of activities. And we can visually see our data and how it looks. We can sort so that we have all the actives at the top and the non-actives at the bottom. We go from low activity to high activity. We can add data filters. For example, I may want to filter to only those values that are of interest. So I added the SST1 column, and I told it I'm only interested in values between 3.2 and 197. And because the sequence table listens to the subset 1, that means that anything I do in this filter affects that table. And I can look at the inactives, or I can look at the actives. I can do multiple filters. I can add a second column in there. For example, I might have a target and perhaps an anti-target. So these are all of the sequences that are active in SST1 but not active in SST2. And we can simply double click in the center to go back to our default data set. On the top tab, there's a little plus sign here. This allows us to add other views. So I can add a second sequence table. I could add, for example, a dendrogram to look at my data to see how related they are, or see if I can identify families in there. And I can add a logo plot to get a summary of my data. In the same way, the logo plot will listen to the filters. If I set it to filter by subset 1, I can look at all of the I can look at the logo plot that is active for subset 1 or the logo plot for the inactives. And using these different views and filtering and coloring schemes, we can easily navigate our data to learn about sequence activity relationships.